this final topic, we're going to look at model performance, and we're going to go through the daily climatic data in Niger to examine this and to dig into this topic of model performance. As a recap, so this data contains daily climatic data between January 1940 until December 1980 for 4 stations in Niger. We're going to use this climatic case study to address the question, is this the correct model? This daily climatic data gives measurements for 4 stations, as we said, and there's multiple elements in the data, I think around about 10 elements. So we're going to construct a linear model. And this linear model is going to predict the occurrence of rainy days, where a rainy day is defined as having rainfall exceeding 0.55 millimeters. So our outcome variable is going to say whether it rained that day or whether it did not rain that day. In our linear model, the following are explanatory variables. So I was a little bit off. There's seven elements there. So minimum humidity, maximum humidity, sunshine hours, wind speed, wind direction, minimum temperature, maximum temperature, as well as station, which is kind of your location, year and month. So we put that in, and here's the output from the linear model after fitting it in R. Of course, I invite you to go through this and have a little look at this in more detail, and to really scrutinize this, and to dig into it yourself as well. See if you were to look at this data, how much do you see how that aligns with this model here? So, for example, we're seeing here that Niamey Aero, so one of our stations, it's not very different to what we've given as our control station. That's not significantly different. So you can check, you can see, okay, how does our number of rainy days look between Niamey and the control station, which name has passed me. So I'll check back here. Agadez, I'm sorry if I'm mispronouncing. So yeah, that first one is looking at the difference is saying that there is not a significant difference in the number of rainy days between these 2 stations. Then as we move to the other stations, we see that there is a significant difference in the number of rainy days between Agadez and Burundi Nokoni, and Agadez and Zinda. We see that for year, there is not a year effect, or there is not a significant year effect. Maybe dig into the data, see what you think, see if you agree with that, because it's always a lot of fun to connect together, piece together what you view through your exploratory analysis and through what the model shows. We see that all of our elements are significantly, very significantly related to whether it was rainy that day or not. Now, to further evaluate our model, we can apply this ANOVA table and see kind of how much variability is accounted for each of our variables in the data. And so through here, well, we see wind speed accounts for a lot of the variability. The month accounts for a large amount of the variability. The maximum temperature as well. The minimum temperature, not as much, which is interesting, but it was still significant here. So that is quite interesting. But we've not given any decimal places. And I suppose our residuals is, well, the F value is still greater than 1, which I guess is why it's significant. Anyway, but yes, we can have a little look at how much variability is accounted for by each of our variables in the model with our ANOVA table. And so how does the model perform? Well, we examine the distribution of the errors term to gauge whether they align with the model assumptions. So one model assumption in a linear model is that the error terms follow a normal distribution. This is kind of covered in the previous topic, back in topic 9. And so we can look at our data and we can see, okay, from topic 9, we saw that if it follows a normal distribution, if our points are along this blue line, then that implies that this model is a good fit. However, here we have a lot of straying from that blue line. This is really quite heavily saying to us, this deviation is really saying to us that we should not be doing a linear model on this data. Again, if we look at a plot of our residual errors against our fitted values, we want this plot to have randomly scattered values throughout. And we can see a two pretty clear, very parallel looking lines. This is not a random plot. This is a distinct trend, which suggests even further that a linear model is not a good fit. So we can see non-normal errors indicating that our model does not meet the assumptions needed for a linear model. So what does this mean? Well, since the assumptions in our model haven't been met, then the p-values in the model are unreliable. This is because the p-values could potentially overestimate the significance, and hence p-values should not be used here. However, this does not imply that the output is entirely unusable in the absence of satisfying our assumptions. It is mainly the p-values that should be treated with caution. What do I mean by that? So we are only doing model fitting when we go to the p-values. So the assumptions only come into play when we calculate these p-values. What we mean is basically an ANOVA is a descriptive process. For example, we're calculating sums of squares and assessing how much variability is accounted for and by which variables. This is the power of ANOVA as a descriptive rather than a modeling tool. The variability remains unaffected. Our ability to access descriptive data is independent of assumptions. So using our ANOVA and those kind of conclusions we've seen from our ANOVA actually are not affected by the fact that our model doesn't fit well, or not as affected by that these ANOVAs are descriptive, and look at how much variability is accounted for. However, when the p-values come into play, then we need to treat it with caution, because we've seen that our model does not fit well. Actually, the model that would fit well here, if you were interested, because we're looking at whether it was a rainy day or not a rainy day, then we have a two-level factor or a binary variable, which means that we should fit a binomial model most definitely. So overall, we can test the model assumptions through plots like a QQ plot. If the model assumptions are not met, the p-values in the model are unreliable. But it's only about the p-values that are unreliable when these model assumptions aren't met. And that's kind of what we saw in the previous section when we looked in topic 9, and we fit to our CALS data, we fit an ANOVA and an analysis of deviance. We saw a very similar result there when looking at how much variability is accounted for in our ANOVA. Was very similar to the amount of variability accounted for in our analysis of deviance. However, we also concluded that that a linear model should not be fitted. Well, as we say, if the model assumptions are not met, the p-values in the model are unreliable, but actually those kind of other bits, if we're using an ANOVA as a descriptive tool, then the variability is unaffected by these insignificant or by these p-values, I suppose. These assumptions. So to get the right model, we need to question if we really need that statistical significance in our context. If we do, We could try alternative models that fit the assumptions of the data. Alternatively, this might be a suitable point to seek advice from a statistician. Thank you.